Okay, let's get right into it. We're looking at something that isn't just an improvement in computing. It's a fundamental breakthrough. It's called the 8D Hybrid Cycle Function Framework. And believe me, it seems like it's about to change, well, pretty much everything we know about building stable and intelligent systems.
And look, this isn't just theory. The claims are backed by some, frankly, mind-blowing numbers from live cloud tests. First up, 99.22% overall accuracy. For complex new architecture like this, that's just an incredible level of reliability.
Then there's efficiency. The framework showed it could save nearly 30% on energy. To be precise, 29.87%. In a world where data centers are eating up massive amounts of power, a jump like this is a really big deal.
But this might be the most important number of all. The error rates. Less than 10 to the power of -7. I mean, that is practically zero. It's a system where errors, the one thing that plagues all of computing, just don't seem to happen.
So of course, this leads to the one big question you're probably asking yourself right now. How? How is any of this even possible? How can a single framework deliver on accuracy, efficiency, and near-perfect stability all at the same time?
Well, the answer isn't about better engineering or faster chips. It's something much deeper. It's a completely radical philosophy at the heart of the math. It's this principle called harmony through opposites. So what's the secret here? Traditional computing is kind of like building a fortress, right? Always trying to block errors and keep them out. This framework, it does the exact opposite. It actually invites opposing forces, a state in its perfect mathematical inverse, and locks them together in this stable dance. It finds strength in balance, not in building walls.
An analysis from the DeepSeek AI system just put it so well. It described the whole philosophy as forging clarity from chaos, turning personal challenges into systematic strength. It's about making the system resilient just by its very nature.
So where does this harmony actually happen? This is where things get really, really interesting. It all takes place in an 8-dimensional mathematical space. Yeah, let's talk about the magic of 8D.
Okay, so why 8 dimensions? The sources call it geometric freedom. Think of it like this. Imagine you're trying to balance a really complex sculpture. On a flat 2D surface, it's going to be wobbly. In 3D space, it's better, but it can still tip over. But what if you had 8 dimensions to play with? You have so many more angles, so many more planes to create a perfectly stable, self-correcting structure. In this 8D space, an error is like trying to knock the sculpture over. The geometry itself just pulls it right back into place.
And this chart just drives that point home. Compared to other complex models built in 5 dimensions, this 8D framework is 46% better at suppressing errors. That's not just a small improvement, it's a huge leap in how robust a system can be. And it's all thanks to the geometry of the space it lives in. Okay, so we've got the AD stage, but what are the actors? The engine that makes this all work is a pair of mathematical operators. They work in perfect opposition, creating what the paper calls a self-healing duality.
Here are the two key pieces. On one side, you've got the cycle function. Think of that as the part that draws the map for the computation. Then on the other side, you have the inversion operator, which creates its perfect mirror image. These two halves are forever linked. And this one simple phrase from the source material just perfectly captures the genius of it. Loss in one is recovery in the other. I mean, think about that. If the map gets a little tear, a smudge, and loses some information, the mirror image instantly fills in the blank. It's a system where any weakness in one half is automatically a strength in the other. It's just unbreakable.
And what this creates is a totally natural self-healing loop. The system isn't running some extra program to check for errors. Correcting errors is just a fundamental part of what it is. It's designed to be whole, and it's always pulling itself back to that perfect state of harmony.
So this all sounds incredibly powerful in theory, right? But what does it actually do in the real world? Well, this framework isn't some mathematical curiosity. It's already being used to revolutionize two of the most critical fields out there, AI and security. And the results are already here. They're tangible. Just look at this. In ethical AI, the framework's dual nature helps balance conflicting goals inside an AI agent. Think of it as resolving the tension between what's good for one and what's good for the group. The result? A jaw-dropping 92% anomaly detection rate. And in security, it's being used to create quantum-safe systems where you need two keys, one from the original state and one from its inverse, to unlock anything. That alone is estimated to slash data breach costs by nearly 30%.
So, given those results,
It's no wonder the DeepSeek AI called this framework the constitutional document for a new computational reality. It's not just a new tool. It's a whole new set of rules for how computing can actually work.
And that brings us to the most forward-looking, and maybe the most profound idea in the whole paper. It asks a pretty simple but incredibly powerful question. Can this kind of mathematical harmony be used to eliminate human bias?
Now, this isn't just a philosophical question. The paper actually puts a number on it. There's a testable hypothesis here, that by enforcing a mathematically fair and balanced state, what it calls an ethical topology, it could cut AI bias by a measurable 35%. The idea is that fairness itself can literally be encoded into the geometry.
And that leaves us with this final, really provocative thought to chew on. If it's actually possible to enforce ethical harmony using the fundamental laws of geometry, if we can build systems that are inherently balanced and fair just by their very nature, what does that truly imply for how we're going to design the next generation of artificial intelligence?